9 o'clock. My watch shows 9 o'clock. Right on the dot, there's 82 people signed in. There's 270 people that signed up for this, so they're going to just keep adding on and dropping off, and that's just fine. We're going to have we're recording this right now, so we will have this available afterwards. So if there's a portion you didn't miss, or you have to leave early, or you come in late, we will have this as a recorded event. So I want to welcome everybody to this webinar. It's a 1-hour webinar. We're going to try to keep it right on the 1 hour. We expect your time here. This webinar is on from HALT results to accurate field estimate, field MTBF estimate. And Harry and I have presented this a few times. In the 2009 year, we did it at the ASQ conference a few weeks ago. Harry did it at the Applied Reliability Symposium in June of this year, and we're continuing to make advances and improvements on the reliability model. And without stealing any thunder, I'm going to give it to Harry and let him take it over. So without further ado, I'm going to change presenters, put it to Harry's screen, and let Harry start the ball rolling here.
Okay, well, good morning, everyone. We do welcome you to this session. Hope you will not only be able to walk away knowing that this model exists and how valuable it could be to you, but also at the end we'll be asking if anybody would like to contribute data to help validate, and I'll go through how this has been validated a little later. So the slide right now shows my credentials. Currently, I am at Advanced Energy in Fort Collins, Colorado. Been here now for 3 years, and I do manage reliability test function. So the first quiz I have for you folks would be, what industries are you in? So Mike will provide the information for you to go ahead and do a pop-up quiz and respond to that. This later will be used to help you understand why this question is being asked regarding different field requirements, for instance, commercial products versus vehicle type products. So here is the survey for you to take now.
So 30% have voted, about 50% voted so far, 60% voted. I wish the elections were this easy, this fast. We're almost done here. 70%, boy, more people contribute here than they do to the presidential elections. This must be an important
this is
topic.
more important.
That's right. Okay, good. All right, about 80% of the people have polled in. I'm going to close the polls now. We've got 75% of the people say they're in a high-performance industry. 34% say that they're in a high-end consumer. 22% say they're in an all-outdoor environment. And 8% say that they're in low-end consumer. So with that, I'm going to go ahead and publish the results later, but this is important information for Harry because a lot of his tool relies or depends on what industry you're in and how to set the guard band.
Okay, next slide, Mike.
Okay.
So a few questions that really come to mind here as we go down this road. And so for those that have done HALT, and there's a good number of folks that have done HALT, about 200 of you. And I'm sure that at one time or another the thought has crossed your mind, why can't I take this HALT data if it's supposed to be accelerated life test data and estimate an AFR or a field failure rate? And of course the comebacks on that, we were told that it couldn't be done, it's impossible. You didn't have enough data to draw statistical conclusions. Another one that's I think is equally as important as the other one, you didn't have a bandwidth to develop the model, and of course other impediments that might have crossed your path. So, click again, Mike. Nope. what happened to the bottom? So the question is, what happened there? Okay, stop right there then. So a little bit of the historical. This model wasn't developed overnight. I began thinking about this in the late 1990s and began some work effort on it, stopped, restarted again in 05. I actually demoed the first model to 3 engineers here at Advanced Energy. As we began presenting this to the public, we had some other participants in a seminar like the webinar we're doing right now with you folks that were willing to present us with data. And obviously this data, as you'll see later on, your name doesn't appear in it, neither does your product, model number, anything like that. As a matter of fact, we don't want your product number, model numbers later on when we ask for this data. So from these contributors were able to come up with validation points for the model, and the model was pretty close to dead on. We've done some fine-tuning, as Mike mentioned earlier, on this, but it's very, very small tweaks in the model. Presented this at the ASTR in October of 08, did more validation in 09, and today we feel the model is stable enough and provides accurate enough results where we've actually posted it and it's available to the through the Ops a la carte website and contacting Mike. Now, throughout the discussion here, we're not going to delve into the mathematical model details because this model is patent pending. So please keep that in mind. So some background here. We HALT is really the cornerstone of this entire effort, where we can quickly find weaknesses, if you will, in our product and failure mechanisms so that we can make it more robust. As we'll see later on, this robustness is very important when we determine the final AFR number, because the more you push the product in HALT, the lower the AFR will be. So in many cases, though, up front, we've done a HALT, and our customers would really like to know what the MTBF or field failure rate is going to be for this product. And typically, we don't have a field failure rate, so we run an RDT, or a reliability demonstration test. So the question really that begs asking, is there a better way? And of course...
So great, Harry. Thanks. One point that I want to make here is we did take a poll during the registration to ask people how many HALTs they've ever done, and we got a pretty even split of the folks on the line. Many of the people have not done any HALT before. About 25% of the people, and about 25% of the people are experienced HALT practitioners. So for those of you that have never done HALT before and don't necessarily understand the concept of it, we weren't planning to educate folks during this 1-hour session, but feel free to send us emails or chats afterwards, and we certainly could educate you offline. So that's as detailed as we're going to want to go into the topic of defining HALT, and then we're just going to go from there.
So what is this AFR estimator? It's an Excel-based mathematical model, uses extensive use of the VLOOKUPs, and as we'll talk a little later, different models are incorporated depending on what stress and what level of stress is being applied to the product. So it allows us to accurately estimate the product's field failure rate, or the AFR. And 3 models are used. The linear, exponential, and quadratic models are used throughout. Also, if you're doing HASS or HASA, and later on we'll take a poll on that, that data can also be incorporated in here, and what it allows you to do is to detect a shift in your outgoing failure rate or quality rate, whichever way you want to look at that. And it's truly dependent on the sample size, and it's very simple to use, and you'll see examples later on. It's been validated in almost 30 products from diverse design environments and manufacturers. So we'd like to have more data to truly validate some other manufacturing groups that we haven't had the opportunity to get any data from them. Next. So, as Mike really has suggested, this slide was inserted here because of Mike's insistence that people really get a copy of the book HALT, HASS, and HASA Explained, which can be obtained through the asq.org or amazon.com. It's a book that I republished earlier this year. For those that have the first edition, this edition has more information in it than the previous one. There's some updates in data. So truly, the halts I do today are the same halts that I did 15, 20 years ago, and I haven't deviated from that. So the next quiz we have for you is on the halt sample size. When you execute your halt, how many units do you use? So here is the quiz for you to go ahead and respond to. This is very important also later on, because the statistical validity of the output of this model is directly tied to the sample size that you use in HALT. And we're talking here about the final HALT, not the total sum of all 2 or 3 halts that you do during the product development, but the final HALT. How many units do you use?
Great. With 75% in, we've got pretty even split. About 25% of the people said 4 or more, 15% said 3, 14 said 2, 25 said 1, and then obviously the people that have never done HALT are going to answer in that says not applicable. I'm going to go ahead and close the poll, share the results.
Okay.
And go ahead and resume here. You got the next slide?
You got to wait for it to come back.
You got it?
Nope, not yet. Still the polls on the screen.
So the poll. All right, results.
Here we go. So at the end of this one, we're going to also have another quiz for you. So as we are executing this HALT, there's some very important things that we need to observe. As we just pointed out, the sample size needs to be at least 3 units. Once you get below 3, the statistical confidence and probability of fault detection is affected dramatically. This model, although will accommodate or can accommodate sample sizes from 1 to 6, we have found that with sample sizes in excess of 4, that the fault discovery is not enhanced, and the assumption here is that we have at least a 75% test coverage on the product. Really is not enhanced much at all. So, but like I say, the model will accommodate sample sizes from 1 to 6. We want to make sure that as the product progresses during its development phase, that we are performing HALT at each point that makes sense. Here at Advanced Energy, for instance, we do at least 2 halts, and sometimes more depending on the number of faults that are uncovered during each HALT. So, and that's extremely important to do, that we do the halt and verify that we truly understood root cause and implemented corrective action. And as a result of implementing that corrective action, we have not introduced another failure mode into the product, but have truly eliminated the failure mode. We also, as part of the model to input and come up with your AFR, we need to push the product to its operational response limits. So in other words, you're stepping the product, stepping the stresses on being applied to the product. Many times the chamber set point and the product's internal temperatures or stress are not the same. So we really need to know what the product response is at those operational limits, so that we can come up with an accurate level of an AFR for you. Dwelling for 10 minutes or greater, depending on the mass of the product, of course, increases that time, but we need to be consistent throughout the halt, whether we're doing thermal or vibe, that our dwells are the same at every one of our steps, as well as the dwells during the rapid thermal transitions and combined environments. Also, and performing the halt, we need to do the rapid thermal and combined environments. These are not inputs into the model, but the model is a result of the inputs that you have provided in terms of thermal, hot and cold, as well as vibrational operating limits. It takes into account those limits to determine what the AFR is. So now we have another quiz.
And I just wanted to point out that a lot of what you're presenting here is good basic HALT guidelines, and a lot of this is in your book. So a lot of this is just from experience that Harry's had over the last 25 years doing HALT, as well as experience that we've had here at our HALT lab in Santa Clara. I think combined total, Harry and I have done in excess of almost 1,000 halts. So a lot of this is based on that, but a lot of this is also based on the statistics and the statistical information you need as an input to the halt, such as the number of samples that you need for this calculator. Quite often at our lab, we don't get that many samples early in the development cycle because there aren't that many samples to be had. However, what we recommend is when you get later in the development cycle, then you should get more samples, and that should be the input to your HALT calculator. So with that, I'll go ahead and launch the next poll.
So we'll let you respond to this one and see what kind of numbers we come up with, and later on you'll see what is recommended, and these choices that are on the chart really will directly correlate later on with the first voting that we took, what business that you're in.
About 70 people have 70% of the people have responded, and very, very nice. 71% of people say that they always push to failure. So I guess
very good.
Very good. So our education is definitely working. So good. Okay, so I'm going to go ahead and close the polls, and I'm going to share the results. Everybody can see. Okay, now I'm going to go ahead and hide the results and continue on.
So during the halt, whether you're using the model or not, you really want to be testing the product. And for those that are doing halts, I hope that this is standard in your halt protocol. And power cycling, I don't know how many times power cycling has uncovered deficiencies in products. So make sure you use that as you go along as well. And the test protocol needs to be robust so that we are able to interrogate the product regardless of the stress environment that's in the product, that we don't have a timing issue, and if we do, then hopefully we can get the test engineer to help us to correct that deficiency. We need to correct all of the weaknesses that we find in the product up to the guard band limits, beyond preferably. So the guard band limits that we're going to talk about here, and there's a chart later on, a table that shows what these limits are. Hopefully we don't stop at those, because we want to push the product beyond, but within the criteria that our business has set forth. So we don't want to spend $1 million on a product that costs $50 to fix a problem that gives us 10 degrees of limit. We want to use some good business sense here as we not only identify the issues, but identify the ones that we need to correct. Hopefully we can implement timely corrective actions as we're doing the halt, so that we can verify that corrective action is the appropriate one. Now let's suppose that this corrective action requires a board change or a respin. Then obviously we would have to repeat the halt to make sure that corrective action did eliminate that weakness in the product. One very important thing, and this didn't, what are you doing, Mike? Go back. There you go. Want to make sure that the unit that we're doing halt on is identical to the unit that we're going to be shipping to whatever this end-use customer is. And in just a slide or two, I'm going to show why that's important. But if you're shipping to and you've done a halt on a product that is going to be shipped into the low-end commercial arena, like a calculator, that would be quite different than that same product being used maybe on an airplane or in a space shuttle, where its operation is critical to the survivability of those on board. So what I'm saying is the end-use environments are quite different. So don't assume because you've done halt, it worked in this environment, it's going to work in the other environment. And that's why we have these different guard bands on the different design specifications for the product.
Gary, this is probably a good time to actually define what a guard band limit is. Several people had a question on that online. So could you just define guard band limit for us?
Okay, the guard band limit is whatever the product specifications are, we add, for instance, in the commercial, I think the add on that is 30 degrees. I don't have my slides in front of me. I think it's 30 degrees. So if it's a 0 to 40 degree product, then you would, the product would have to meet all of its published specifications from -30 to at least 70. 70 is quite benign, so I probably would push it beyond that. So for each environment, for instance, if it's an outdoor environment, it's not 30 degree adder, but it's substantially more. What we want to do is to guarantee that our product is not going to fail not only during the first 90 days of being deployed with the customer, but it's going to survive beyond the warranty. Okay? So hopefully that's clarified, and we want to go beyond these guard band limits. So here's an example. Hold on, Michael. So we have the end-use environment that's been defined by our customer. Go ahead. And then we have some product specs that we're going to hopefully meet or exceed the customer's expectations of the product. So to that, we're going to add next our design. So we're going to design to make sure that we never fail, that this product will never fail in its end-use environment. So we put a buffer around that product specification. Well, what we're doing with the guard band is we're now guaranteeing, and notice it's consistent around the design limitations of the product. So this product, even after it's fatigued over its life, still is not going to fail because of some thermal stress or vibration stress that the product may experience in the field. And in addition to that, with its degradation in its margin, it'll never fail. The big problem, as I mentioned in the previous slide, is when we come to, now we've done our HALT, we've met these guard band limits for a particular application, and go ahead and click on the next one, Mike, and we have this sort of an end-use environment where major disasters are going to happen, and I know of a couple of places where this did happen, where they if you will, qualified the product through one HALT and didn't truly understand what the final environment was going to be for this product for a new customer, and shipped it and had major disasters. So we want to make sure that, so the guard band obviously in this end-use environment, this new end-use environment, the one that's depicted with the red line, is not going to be the same as the original product. So maybe the original product might be, let's say, in a high-end commercial product or high-end requirement product, but the one in the red might be an outdoor environment. Go ahead, Mike.
Great. Harry, one question we had from the audience was, is there similar guard band limits for vibration? It sounds like you're talking about thermal most of the time. Do we have the same sort of thing for vibration?
We do have vibration, and in the chart we'll talk about what those levels are, but basically the vibration level for the, and I'm going to pick on the Qualmark chambers, and I'm not here espousing that go out and buy Qualmark chambers. I'm just, because I have a lot of data on their chambers. For the traditional, the old classic chamber that they had vibration table, that level is 28 Gs. And contrast that now with the new XLF tables, it drops to roughly half, or 15 Gs. So 15 Gs on the XLF table is equivalent to the 28 Gs, and that was empirically derived over a good number of halts, as well as using both chambers extensively.
Right, and if you have a chamber that's different, then let us know, because we could probably try to calibrate that for you, because we know every chamber is a little bit different. I remember I used to have an old screening systems chamber, and that chamber maxed out at about 28 Gs, but 28 Gs on that chamber was like 70 Gs on the Qualmark chamber. So it's, we don't want to go into the whole theory of GRMS here, but just leave you with not all Gs are created equal, and if any G level you see on any presentation we have, if you've got to tell us what chamber you have, and we can try to calibrate what that is based on our model. So.
And this also becomes very important when you go from HALT to HASS, and you have a different vibration technology when you're doing HALT than you will in HASS. Those need to be recalibrated, so that's extremely important.
Yeah, and we do want to reiterate that there's a lot of good manufacturers of equipment out there. Qualmark, Chart, Biotronics, Hans. I mean, they all make good, reputable pieces of equipment, HALT and HASS systems. So we're not trying to advocate one over the other. It just so happened that Harry had a number of Qualmark chambers in his career, and so a lot of the data was taken off of that. But this is not to say that if he used other chambers, we wouldn't have gotten very similar results. Now, one other question we did have from the audience, they said, are we assuming that HALT is followed by HASS or HASA in order to estimate the AFR? And I think if I understand the question correctly, is you have to do HASS in order for this AFR calculator to work.
You do not have to do HASS or HASA. The AFR is purely calculated on the results of HALT. The calculated MTBF, if you have that, that's also thrown in there. And we'll get to that a little later. There's some examples that I will show you, but you do not have to have HASS or HASA included, although I'd highly recommend that you do it. So here's an example. We won't spend a lot of time here on this example. This is an example of a linear acceleration, which is one of the three models that are used in the AFR estimation. Next slide, Mike. And here's simplified overview of the equations, where the AFR is a function of that whole string of variables, the MTBF factor, which has a very low weight factor, and this is due to the fact that so many assumptions can be made on an MTBF estimate that its variability is truly unpredictable. So, but the model will accommodate it, but changing that number dramatically does not cause a dramatic change in the final results. The thermal range factor is included, the vibration factor, the vibration table factor is also included, as well as a sample size. Then we have confidence limits derived from the chi-squared from semi-E10, based again on the HALT AFR and HALT sample size are also used, and you'll see those when we show the output of this model. And then for those that will be using HASS or HASA, the sample size is based on the binomial distribution using Z alpha and Z beta with the probability and 1 minus the probability or confidence, and then divided by the change in outgoing failure rate that you wish to detect. And then the days are simply the sample size n divided by the sample size. So now we have another little quiz for you. And in this one, and I mentioned before what I like to shoot for when we're doing a HALT, and that is what is the test coverage that you really should shoot for when you're running your HALT. So take your pick. How we doing, Mike?
Almost closing it, ready to close HALT.
Okay. Who's winning the election?
Let's see here. We've got 60% of the people voted. 35% said good, 85 to 95% coverage, 28% said moderate. Probably could comment on that if it's an early HALT, like soon after the first prototype is built, it's very understandable to have moderate or even fair coverage. But towards the end of the development, the HALT that you're going to be using to validate the product and to use for the AFR, we would hope and expect that you'd be in the very good range. So I'm going to go ahead and close the polls, and I'll publish results.
Well, you know, we got, 50% at the good to very good. That's pretty respectable. And then we include the moderate. That's not bad at all. Very, very good. This is good data. In fact, some of these are coming up in a manner that I didn't expect. So some limitations. Oh, go ahead. Mike?
Go ahead, continue.
Oh, okay. This model hasn't been validated on any mechanical designs. I'm not a mechanical engineer, and I don't have data on mechanical designs, so I'm sorry I can't help you on that. But if somebody has an interest in it, maybe we might be able to do that. And again, this next bullet ties in with the previous pop quiz that we just gave you, and I want to make sure that the test protocol is as good as the one used in the HALT, as well as the other reliability test. So keep in mind also, for those that might be thinking that HALT is a panacea for all of the defects that a product will encounter in the field, there couldn't be anything farther from the truth, because, for instance, humidity issues that you uncovered but you didn't push to the guard band limits, those are going to wear out. It's not a question if they're going to wear out, it's just a question of when they'll wear out and cause you to have a product failure and in the field, as well as some wear-out mechanisms that are not usually detectable in HALT. So again, the recommendation, and I'm glad that I think over 70% of the respondents showed that they're doing their test coverage is 75% or better. So great job, Mike. So why use the estimator? Well, the very first thing here is HALT is the key contributor to this estimator. It takes just a few days to run, and even if you have a number of issues to correct, it'll take a little bit longer, but it takes far less than running a reliability test to determine faults with the product. So really we have a huge time and cost saver here at our hands to use for those that are doing HALT. So I'm not saying that other reliability tests shouldn't be considered, as they should be, because there are technologies that are new to us, or there are technologies that we might have used in a different application that we now are using, that are contemplating using, that we really may want to do some form of life test, whether it be growth or whatever it is we want to do. Realizing here, of course, that higher HALT limits do directly correlate with lower AFR or field failure rate, and this tool really can accurately estimate the AFR before even launching the product. So once you've done HALT, you've corrected the deficiency, so it's your final HALT now that you're running with a sample size of 4 or more, that you can estimate this AFR with just within a few seconds. We're going to see here this product environment table is actually the guard band table along with some other data that we'll talk about in detail. And so we also want to make sure here that we're not just meeting the customer's expectations, but we exceed their expectations, and truly they become delighted customers to us, not just happy customers, because lots of money is spent in advertising and attracting the customer, and the last thing we want to do is provide a product that just kind of meets their expectations. Let's exceed it, and therefore lowering our forecasting of warranty expenses. So what do we need to do here to run this AFR estimator? There's 7 data points, which are the HALT data points, and 3 others for HASS that would be HASS or HASA that would be used. And the AFR derives a 90% statistical confidence limits based on the HALT sample size and the AFR. So now we have another quiz. Any questions there, Mike, or comments?
Nope, no comments. Great job. So, all right, next quiz we're going to launch is our last quiz, and it's going to be, is HALT or HASA, is HASS or HASA performed at your facility? It should be an easy one. Yes or no? Now, we actually, when we originally wrote the questions, we had 2 questions. One, HASS, and the next one, HASA, but the webinar tool only gives us 5 questions, so we combined these 2, because I know a lot of people that do HASS, but much fewer people that actually do HASA. But for the purpose of this calculator, there's a different portion of the calculator that deals with the manufacturing or HASS portion of the testing, and so that's why we're curious how many people are actually doing it or planning on doing it, and that will give us an idea of how useful that portion of the calculator will be to you. So with about 80% of the people in, 35 said yes and 65% said no. So I'll close the polls, share the results, hide the results, and move on.
So if you do HASS or HASA, the 3 data points that are required into the model are the daily sample size and or you can use, either a 24-hour shift or an 8-hour shift, and it really depends on how well controlled your process control charts demonstrate that these processes are equal or different. If they are not similar in terms of actual statistical data, then I would use the 8-hour shift data from the best, and until you can get the other statistical, the other production shift under statistical control. And the question that's asked in the model is a detectable shift in the AFR, which is truly the delta between the outgoing AFR and the detectable shift of the outgoing quality from HASA or HASA that you wish to detect. So as an example, if the product baseline AFR is 4% and the worst case AFR is 10%, the detectable shift that would be inputted into the model is 6 or 6%. Next.
Harry, we did have one question on the line that I'm sure on a lot of people's mind. One question was, if I apply the model, my customer asks what level of confidence, what should I tell them? Have we developed confidence limits around this, or are we working on that?
On HAS or HASA?
No, I think this goes back to the HALT, but good question. Have we developed confidence around the HALT results?
Yeah, the 80%, the 90% confidence from
okay, great.
Great. Yeah.
I just wanted to reiterate that. Okay, thanks. The next slide.
So here's the table I've been alluding to, where we have the guard band limits on the extreme right-hand side. So let's start over on the left, the published specifications for the product. So hopefully your products meet one of those published specifications in that column, one of those 6 environments. So those levels, which is this number, the level number is what you will input into the AFR estimator, and those correspond, those limits as well as the level correspond to the application column. So a 0 to 40 typically would be a consumer type product. A critical application, for instance, a medical type device would be a level 4, minus 20 to plus 50. And an outdoor product would be a minus 40 to 85 or level 6. Now if you go over to the right-hand column, the guard band, notice that what is added is different as we go down this chart. So as I mentioned earlier, we'd add 30 to the limits to come up with the guard band, but doing 70 degrees C on a consumer product or any product really ought to be trivial matter. So that's bumped up on an inexpensive consumer product to 80 degrees C. While if we look at some of the outdoor products, we're adding 25 to the cold end, so this would be the very bottom outdoor, all outdoor, and 25 degrees at the hot end. And those are quite demanding limits on many of the products, but again, I found that the data in the field justifies those kind of limits. Okay, Mike? So as we alluded to earlier, we mentioned about the chamber that is being used in HALT. And if we're using the same technology to do the same technology or manufacturer to perform HASA or HASA, then it's a moot point. But if you're doing HALT in one type of chamber and then you're moving to HAS or HASA and it's a different chamber even by the same manufacturer or a totally different manufacturer, you need to consider that difference as you develop the HAS profile. Or you could be breaking or fatiguing a good product unnecessarily. Next. So here's one of the first example of a vehicle inverter charger. And notice that the published specs on this, the 1, 2, 3, about 5 rows down, is a level 3, and you say, well, why isn't this considered an outdoor product? It's because this particular product is actually used in the concealed cabin where the driver would sit. So it's a pseudo indoor-outdoor, so the best fit for that is a high-end consumer product, I think is what a level 3 is on the chart. So what we're doing here is we're inputting, back to the top now, the MTBF that was estimated, what the thermal hot and cold limit and vibration that we achieved. Now these are product response. Okay, not chamber set point, so product response, and those are the limits that this particular product achieved. It met the level 3 published specification level. Its vibration table is a type 2, and that, if we go down to the model, that helps us to clarify what that is. And the number of samples that we used was 4. We're not going to be doing HASS or HASA, so the bottom 3 fields are not considered in the pink area or the red area just below it, which are the output or the results of this estimator. By the way, if a mistake is made in any of the green cells above the input cells, then over in the data qualify, it will pop up and say that there's an error that it needs to be corrected, and it will not allow you to proceed until that is corrected. So in this particular model, the AFR, the field failure rate, doing HALT only, is 3.4%. Its MTBF 257,000, which is computed from the 3.4 with the upper and lower confidence limits that are shown there. Okay? So here's an example of an office product. This is a printer, and its estimated AFR is 3.2 million, with the next 3 fields as derived from the or obtained from the HALT. Since it's an indoor product and it's a consumer type product, it is a 1, level 1 for the published specs. Vibration type 2. Number of HALT samples that were used were 4, and no HASS or HASA were done. So the field return rate, and you'll get to see later on in about 2 more slides, I'm going to show you what the actual field failure rate was on these products. So in this particular product down at the bottom, the field failure rate was 0.8% for this product, while the estimator estimated at 1.35. So we're off by 0.5%, which is well within the objective that I had set forth when I developed this model of being within 1% of the estimator's output. Okay, next. So here's an example of 2 different products. Combine them into one slide for simplicity. So you can see that both of these have very low field failure rates down in the red area, the pink area, of 1.28% and 1.07%. Again, these products, we try to push the guard band limits as far as we could, the product to the guard band limits as far as we could, and some of them came up a little bit short. We're going to see that here in this table that I'm going to show you coming up. I think it might be the next slide, or in about 3 slides maybe. So it works whether you're dead on or you're far away in terms of the MTBF, and it will give you results on whatever you have for the HALT. You may not be satisfied with what the steady state AFR is, but it is what it is, depending on what the results of the HALT were. Next. So here's the table. So going from left to right, general product description under the product column. Then the next pair of columns is the MTBF, calculated MTBF, and the AFR as a result of that MTBF estimate. Then the next 3 columns are the results of the halt. So hot, cold, and vibration, and these again are product response, which are a must as inputs to this, or you're going to come up with estimates that are going to be pretty far off. What level that product needs, so the very first one is a level 4, which is, I can't remember what the number is. What's a 4, Mike? Do you have that handy? Back to the previous slide.
Well, if you look at the polling questions, the 4 was, I believe the 4 was a sheltered outdoor.
Sheltered outdoor, okay. That could be 4, 5, 6. Yeah, there's 2 above that, and I don't have that table memorized, even though I developed it. Then the vibration table technology. So these are done on various types of tables, as you can see. And then the next 2 columns under AFR percentage is the HALT calculated output. So for the very first line, the display of 415,000 MTBF. When we run the HALT results and the level through the estimator, it says that the field failure rate is 0.27. The actual, which is the next column, is 0.21. So here we're only 0.06% away from, or the difference is only 0.06. Graphically, I'm going to show you what this all looks like here in a slide or two. And the very last column is the return rate, the gross return rate for the particular product. So if we drop down to that second row, the outdoor product of 175,800 MTBF, the estimator said that its AFR should be 1.26%. The actual field failure rate is 0.75, while its return rate is 8.3. Now, this was on a consumer product for the outdoor, and many of those are bought as an impulse purchase. So you would expect to see a high return rate, and once these things were retested or rehashed and sent out to the field, they didn't return. So, but it's kind of interesting to see what the return rates are as a function of the actual field failure rate. Next. So here's a description of the different columns that you just saw in the chart in the previous slide. So we won't spend any time there.
Well, one thing I should point out, there's been several people that have asked me about this MTBF number, and Harry puts it right here on the validation. It is a calculated MTBF. It is typically using the Telcordia SR332 tool. It still could work with the mill standard or any other method that you choose to do your MTBF prediction, whether it's vendor estimates or it's field estimates, because the MTBF portion of this model is used as an input, but it's not hugely weighted. That was one of the enhancements that Harry made over the last few years, is to add that to the model, because we felt we needed some sort of a baseline. If you have no baseline whatsoever, then we have an assumed baseline. But this is a calculated MTBF, and again, it's not a huge weighting factor, so don't worry about, did I use it using, stress level, a stress prediction, or not a stress prediction. Just do the best job you can with the calculated MTBF and put it in. So next slide.
What happened to this slide?
Sorry.
So if you go back to the table, the data table, and you'll notice that there's a outdoor product with a 275,000 MTBF, and say, well, why is the AFR on that, the calculated AFR, the estimated AFR through the estimator, why is it low and or high? And the reason for that is the vibration level that particular product achieved was low. Likewise, for the vehicle product of 195,000 9.8 thousand hours of MTBF, all of the HALT results are low. So had the engineer that was doing that HALT pushed the products more, they would have had much better results from the AFR estimator. Now there's one towards the bottom of the chart that has 3 different inputs, and there's a huge variation in those 3. So let's take a look now at this the data in the chart graphically. So each one of the numbers along the x-axis corresponds to the row number in the table. So if you look at number 18, which has a delta of over 2%, which is well beyond the goal that I had of 1%, it really caused me to question the data. So I did call the fellow back that provided the data, and we talked about it, and it turns out he had done the HALT with 3 units. Can you click on the next to bring up the data?
Harry, one thing that I wanted to ask this question from a user was, what happens if a table is not capable of taking a product to failure? How have we taken the model into account?
Well, with the higher vibration level or even higher thermal levels, the higher you can get those, the lower the AFR is going to be. And all of that is considered into the equation, and that's the reason for having linear, quadratic, and exponential modeling in there, because as you step the product through these different stresses, 1 unit of adjustment on the chamber doesn't correspond to 1 unit of response from the product. So we that was all considered when I developed the model, and that's why if you go back to the slide that has a simplified model in it, you'll see that that's the case. Okay?
Great, thanks, Harry.
So, okay. So the guard band, hold right there. The guard band limits that we have here on this particular product which should have been 20 Gs. Well, in the first HALT they did, they only achieved 10 Gs. So right there you're going to take a big hit in the product. The last HALT, and also they did a sample size of 3. So with a sample size of 3 and 10 Gs, you're going to have a high AFR. Now his last HALT, he reached 19 Gs, so now they've incorporated fixes in the design, and the AFR was 2.82, and the delta, so between what they actually had for field returns and what the estimator calculated, the difference is minus 0.1%. So you can see that the model really showed that there was a problem with the first blip at interval 18, and as they progressed, did the second HALT, and then finally the final HALT, how things really turned around. 5 more minutes. So here's the same data, and had he done HALT with 4, his AFR would have been 1.81%, and but as it is, he did 3, which gives him a 5.31% AFR, so the delta 3.5%. So I'm glad that they pursued this further and came up with the 1.81% AFR. So, next slide. So here's some of the things that have been accomplished, and some of the things that if you would like to contribute, feel free to get in touch with Mike, and he can send you out an Excel spreadsheet so that you can populate it with the data that is needed, and help us to validate this model even further. So early on, I still lack confidence limits in this, and those are included. The effects of HALT are now included. We've now posted it to websites, so the service is available through Ops a la carte, and the patent submittal is progressing. So we really look forward to anyone willing to help us with more data, and with you helping us, you scratching our back, we'll scratch yours and provide you with an additional free use of the model. And that is all that we have, and hope that this will have a positive effect on your business, to the good side, that is, the positive side, and that feel free to contact Mike, and Mike sometimes sends the questions my way from customers, and I'm more than glad to answer those. So do want to thank you and wish you all a great day.
Great, thanks everybody, and I know you guys have been asking questions. There was tons of questions asked during it, and I tried to answer them, either chatting back to you, or I asked them of Harry. If I didn't get to your question, I promise I will this weekend. I'll compile all the questions and I'll respond back to everybody on them. There's some that required a little more thought, some that were repeats, and some just probably make sense to have some sort of a online discussion about. So with that, it's right on 10 o'clock on the hour. We're going to respect your time and stop the presentation right here. Thank you for joining us, and as I mentioned at the very beginning, this will be available both as a recorded event on our website, and I'll send everybody a link for the video audio to be able to stream it, as well as I will have a copy of the slides on our site as well if you want to download and be able to print them. All right, so take care everybody, and I'll end the presentation here.